Now we're going to turn our focus to confidence intervals. And the first thing we're going to look at is confidence intervals for the population mean. There's going to be two things when it comes to this. A z-score and a t-score are going to be used. And we're going to focus on the beginning. What if one of these two conditions is met here? Sigma is known, which means we either know the standard deviation of our population or our sample size is 30 or larger. So we have a pretty decent sized sample. The first thing we're focusing on are what is a point estimate? Well, if I were to go through and do a sample, the mean that I get from that sample would be my best point estimate. For example, if I survey 50 people and I find that their average pulse rate is 72.3, that would be a point estimate for the population's pulse rate. Three properties if it's a good estimator. The first one has to be unbiased, which means the expected value is equal to the value that I actually get. So what ends up happening here is the number that I get, the mean that I get from my sample, matches the mean of the actual population. It's consistent. As the sample size increases, the value of the estimator approaches the value of the parameter, meaning this. We know that a small sample could have us pretty far off of the mean. I could easily go out and interview 5 people and end up with an average height way above that of the regular population. But as I interview more and more and more people, as I increase my sample size, the idea that my mean of the sample is going to become more close to the mean of my population. And relatively efficient, of all statistics that can be used to estimate the parameter, the best estimate has the smallest variance. In this case, we're talking about variance being difference. How far away from the mean is it? So we're going to do an interval estimate here. Okay, what we're going to do is we're going to develop an interval. This interval may actually contain the mean of the population, but it might miss. The question is, how confident are we in our prediction? A lot of times we'll deal with 95% confidence intervals, we'll see 90%, and we'll see 95%. They're not the only three, but they're the ones we'll spend most time on. So what does that actually mean? That means that we have a 0.95 probability of the interval that I find contain the actual population mean. This means that if I were to do a sample 100 times, 95 would actually contain the population mean. Some are going to miss. This isn't a perfect situation. And then we have some formulas here. This is how we're going to find the confidence interval. This is how we're going to find our margin of error. Notice that these two pieces are the same. And what if we know the error we're willing to accept? How are we going to figure out how large our sample size has to be? Our first example here. So let's look at this situation. A local realtor is researching the value of houses in his hometown. He finds the value of 40 houses, I'm going to write my n value down, have a mean, this is a sample, so x bar, of $289,700 and a standard deviation of 54,600. Now in this case, my n value is larger than 30. So I'm going to be able to use a z-score. When I talk about a point estimate here, the point estimate of the mean is just this value. So the best estimate I have of how much a house actually valued at in this hometown is $289,700. The exact same number I get from my sample. Point estimate is just simply one value that indicates the population mean. Now we know that this is accurate, but how accurate? Is it exactly 289,700? Most likely not. It's probably just in the vicinity. So now I want to start to develop an interval. The interval will give us a between here and here. So now we'll be able to decide, where is this? It's hard to say it's one value, but if I give a range of values, we're more likely to fall inside that range. We want 95% confidence. Confidence intervals are two-sided. So what I'm looking at here is I'm cutting 5% off, which means I'm cutting 0.025 off both sides. I put this in the inverse norm, and I have to find my z-scores. Well, my z-scores are going to be positive and negative 1.96, with the negative being on the left and the positive being on the right. This 1.96 is the z-score number that I'm going to use here. So go back and look at the formula. The first thing it takes in is your x bar value, so 289,700. Then it says plus or minus your z-score, the 1.96. How far away from the mean are we going to go? Take your standard deviation and divide by the square root of your sample size. In this case, the formula asks for sigma, but because our sample size is large enough, it's okay to say that those two are equal to each other. The sample standard deviation is the same as the mean standard deviation. I multiply this out. This right here, this piece, is my margin of error. When I multiply that out, I'm going to get $16,920.70. This represents how close I'm going to be to this number for my mean. So now to find my confidence interval, all I have to do is take my margin of error, the 16,000, add it and subtract it to my sample mean. When I subtract it, it's going to give me a house value of $272,779.30. When I add it, it's going to give me a house value of $306,620.70. So what we're looking at here, this is my confidence interval. I am 95% confident that the true value of a house in this neighborhood, the real value, average value of a house in this neighborhood, will be somewhere between these two values. Let's look at our second example. In this case, we're looking at an English professor who's grading 40 papers. He spends an average of 12.6 minutes grading these papers. And from previous research, we have a standard deviation from the population. We have a large sample, and we have standard deviation from the population. So we're going to clearly use z-score here. Remember, this is a normal distribution. It's 90%, so I'm cutting 5% off both sides. This is where you'd use your inverse norm. This over here is 0.05. Use that number. This is going to give me a z-score of positive and negative 1.28. Negative being on the left, positive being on the right. All I'm going to do now is take my average that I found from the sample, add and subtract my margin of error, which is my z-score, how far away I'm willing to go, my standard deviation, divided by the square root of my sample size. The n part over here should look very familiar, the 2.5 divided by the square root of 40. That's what we looked at for the normal distribution with the central limit theorem. And again, this whole piece is going to give me my margin of error. My margin of error in this problem ends up being 12.6 plus or minus 0.51, which means we are 90% confident that the professor will spend 12.09 to 13.11 minutes grading each paper on average. We're only 90% confident. We may have missed that. It may actually take longer or shorter than this interval, but we're 90% confident that it's in there. Second problem, if the professor stated that he spent on average 30 minutes grading a paper, what would your reaction be? This number is nowhere near inside this interval. So if the professor said that, you would easily be able to say, if this is true, there's no way you spent 30 minutes. And our last question says, how are we going to look at sample size? What if I know the margin of error I want? In this particular case, he's estimating the monthly salary of sports reporters, and he finds a standard deviation of $1,100. We want to be within $150. So we want to figure this out here, and we want to be able to figure out what the average monthly salary for a sports reporter is. Well, we want to be within $150. So this is our margin of error. And we're looking for how big our sample has to be. We want 90%, which we just found in the last problem to be positive and negative 1.28. In this case, you're only going to use the 1.28. You do not need the negative, just the 1.28. Let's look at our formula. And plug in what I know. I know my z-value, 1.28. I know my standard deviation, 1,100. And I know I'm within $150. This is squared. I end up with an n value of 88.1. 88 would be too small a sample size. It can't be 88.1 because we're looking at people here. So I'd have to round up. In this case, I'd have to interview or survey 89 sports reporters to be within $150 of the true mean.